We've looked at kinematics in the past when we studied differential calculus, but there's an application of integral calculus in studying the linear motion of objects. So let's revisit our study with derivatives. So if we have a position function giving us the position of a particle at any time t being t squared minus 4t plus 1, what does s of 0 find us? We substitute 0 into this, we get 1. What is that? That's the initial position. And what would S4 give us? S4 give us the position of this particle when 4 seconds have gone by. And if we substitute 4 in for t, we get 1. So the displacement in first 4 seconds is 0. Would be the position at 4 seconds minus its initial position at 0 seconds, or 1 minus 1, which is 0. Well, S4 minus S0, that looks strangely like the evaluation of a definite integral. The integral from 0 to 4 of, well, what function has an antiderivative that is the position function? Well, it's the velocity function. And in general, if we know the velocity function, we can find the total displacement by integrating the velocity function with respect to t and evaluating at the beginning time and ending time. So let's change these end values from 0 and 4 to T1 and T2. So in general, this is our displacement. Important. Okay, now let's go back to, that didn't even need any calculus, but I brought calculus into it. What about total distance traveled? It's a little bit different game. We need to know when we might change directions. And we're going to change directions when we're traveling when the derivative of the position function, that is when the velocity function, equals 0. So this is a change in direction. So v of t will be the derivative of the position function. The derivative of that position function is 2t minus 4. If we set that equal to 0, we find that at t equals 2, there's a direction change. So if I draw a motion diagram for this, there's 0, 1. Our particle starts out right there at 1. And then at 2 seconds, it changes its direction. And if we did a sign diagram, if we substitute 0 in for our velocity, we get that the velocity is negative on the left of 2, and it's positive to the right of 2, which means we're traveling this direction to start. And then at 2 seconds, we turn around and we start going back this way. So where are we at 2 seconds? What is s of 2? At 2 seconds, we are at a position of negative 3. I'm substituting back in right here. So I get to 1, 2, 3, right there. So my path of travel starts out at 1. I travel here, and then I change directions. And I already know that at t equals 4, I'm back at 1. We saw that earlier. And this is t equals 2, we're at negative 3. And I know this is the only direction change at time equals 2 because that's the only place that the velocity is equal to 0. So what's my total distance? My total distance would be 4 that way, and 4 that way, my total distance is 8 units. So how can we relate this to integral calculus? Well, our total distance would be the velocity times time. That's distance, right? Distance is velocity times time. But we have to think of this as a whole bunch of distances that we're going to add up. We took this 4 and added that 4, so we're going to take the sum of the velocities times time. But you might be saying, wait a second, some of these velocities were negative. We were going to the left. And if I have my negative velocities going this way, we call this -4, and that way +4, and we get 0 for the total distance traveled, not 8, Mr. Schnack, and that's a problem. And you're right, it is, because that's finding us the displacement. What we need here are absolute values for the velocity. And when we add up a bunch of these velocity times time, we let that time interval shrink, so we're finding the instantaneous velocity times the instant in time, and we're adding these up. Now we're entering the realm of calculus. We're going to do t1 to t2 of the absolute value of the velocity function times dt. And this is the total distance. And we have 2 examples to look at today. And I hope that seeing these, what we can do with this integral calculus makes this question a lot easier than having to draw these motion diagrams, which you do need to know how to do. So we have a graph here. It is our velocity function, v of t. I want to know what's the total displacement in 16 seconds and what's the total distance traveled in 16 seconds. 2 different questions. Now, we said both of these can be expressed as an integral. What do integrals find us? So for the displacement, it's just going to be 0 to 16 v of t dt. Well, but I don't tell you a rule here. I can't find an antiderivative, so we have to remember what definite integrals tell us. Well, definite integrals tell us the area under the curve. So what I need to find the displacement in the first 16 seconds are those 3 areas, but with displacement, this area is going to be negative, this is going to be positive, and this area will be negative. So these are geometric figures. We can find these areas using geometry. So this first shape is a triangle. Area of a triangle is 1/2 times its base, which is 2, times its height, which is 4, and I want this area to be negative because it's below the x-axis. This would represent direction to the left, negative velocity times time, plus the area of this triangle, or this triangle has a base of 10 and a height of 8, and that area is positive. That distance traveled is in the positive direction. And then we're going to add on, well, we're going to subtract because this next area is below the x-axis. This is a trapezoid. Area of a trapezoid is 1/2 times the sum of the bases. Well, the 2 bases are 4 and 1 times the height, which is 2. And this area is something that we can just evaluate now. And what we get is 3. The total displacement is 3 units. The distance, however, so this is displacement. The distance traveled will be the integral from 0 to 16 of the absolute value of vt dt. So it's taking all of these areas and reflecting them above the x-axis. So these 3 sections, they're the same shape, but they're all just above the x-axis. So these terms that I have up above, they are all simply going to become positive. So our area would be found by 1/2 times 2 times 4, plus 1/2 times 10 times 8, plus 1/2 times 4 plus 1 is 5 times 2, and this total distance traveled is 29, as opposed to a displacement of 3. Notice what this means. We're traveling to the left, negative velocity. We turn around, we start traveling to the right. We stop, we turn around, start traveling to the left for this amount of time, and then we stop at time equals 16. So this is a geometric interpretation of area representing distance traveled. And remember, it's the area underneath the velocity curve that finds us total distance. Next example, we have s of t given by a function this time, a quadratic relationship, 8 plus 2t minus t squared for all t greater than or equal to 0. What is the displacement and total distance traveled? And how long do I want us to go for here? What's the total distance traveled in, let's go 4 seconds. In the first 4 seconds. Okay, so we could do this using a motion diagram, but I don't want to use a motion diagram. I find it to be inefficient. Using integral calculus is much, 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 much better. So we need the velocity function. That's simple enough to do. We differentiate. 2 minus 2t. Yes? Yes. So to find the displacement, it's going to be the integral from 0 to 4 of 2 minus 2t dt. And that's an antiderivative we can take. 2t minus, t squared, evaluated at 0 and 4. The only difference between this, what we're evaluating, and this that we started with is we don't have to deal with the plus 8 anymore because this is a definite integral. When we evaluate at 4 and 0, when we subtract, the 8s would go away. And so we do our substitution and we get negative 8 meters for the distance, for the displacement. So what does that mean? Well, that means that from start to finish, what happens is we end up 8 units to the left of where we started, regardless of where we went in between in those first 4 seconds. We're ending up 8 units to the left of where we started. For the distance, this is going to be the integral from 0 to 4 of the absolute value 2 minus 2t dt. If I'm going to do this without a GDC, we would need to sketch this graph and look geometrically at what's happening and split it up into multiple regions, that some are that are originally below, some that are above. I'm going to use my GDC though. So integral from 0 to 4. Now I need my absolute value. 2 minus 2, I'll do x, could do t, I'll do t, just to change up things in the calculator. dt, push enter, there we go, total distance is 10. And this should always be positive because it is a distance traveled as opposed to a displacement which shows direction. So that, ladies and gentlemen, is where we shall stop today. The thing to remember, the thing to remember is that for distance traveled and displacement, we are dealing with the velocity function that we're integrating, not the position, not the acceleration, but velocity. And total distance is the absolute value of that. Have a great day. I shall see you later.